Welcome to Taming Your Kiosk Monkey with F5 Distributed Cloud. In this demonstration, I will showcase how you can effectively test, learn, and enhance the resiliency of your modern application infrastructure. By employing kiosk engineering practices, I will intentionally introduce fault into the application and API to simulate failure scenario. This demonstration highlights the capabilities of F5 Distributed Cloud Secure MCN Application Mesh Fabric in ensuring application resiliency across heterogeneous Kubernetes platform, spanning multiple clouds or within a single cloud environment. Leveraging open source Litmus Kiosk platform as the kiosk engineering tools, we will explore the robustness of the application. The showcase applications, Acadia Finance, comprises various microservices distributed across multiple Kubernetes environments. These services such as front-end, back-end, refer friends, and money transfer microservices are critical components of the overall end-to-end application. Litmus Kiosk is deployed on F5 owned Kubernetes variant called AppStack. Kiosk agents are deployed on respective Kubernetes platform and successfully register with Kiosk Center through the F5 Distributed Cloud Application Mesh Fabric. WebSocket connections between Kiosk agents and Kiosk Center is secured and encrypted via a secure encrypted tunnel. Let's delve into the high-level architecture of this demo. Acadia Finance, our modern application subject of our kiosk experiment today, is deployed across various Kubernetes platforms, including EKS, GKE, AKS, and OpenShift Container Platform. Additionally, backend database resides in a virtual machine environment within a separate data center, bridged by F5 Distributed Cloud. Microservices like the front-end, money transfer, and refer friends functionality are deployed on different Kubernetes platforms, while backend databases are hosted on virtual machine. Backup microservices will be deployed onto GKE and AKS via a CI/CD pipeline. F5 mesh containers are deployed and registered on respective Kubernetes platform via the F5 console. These containers facilitate mesh connectivity, service discovery, application delivery, application and API protection, and many more. While in this demo, we focus only on the mesh connectivity, application delivery, and service discovery, please do note that F5 Mesh can also be deployed as a virtual machine nodes to bridge into legacy environment. Once F5 Mesh container is installed, a secure mesh fabric is established, connecting Kubernetes platform either through F5 Regional Edge or POPs in a hub and spoke topology. Administrators have the flexibility to customize this fabric into a full mesh topology. Secure Mesh Fabric works as an overlay secure encrypted network to facilitate and orchestrate connectivity between those Kubernetes platforms. Acadia Finance application is accessible to user, bot, and unwelcome adversary via the F5 global network, ensuring the connectivity and availability. To simulate kiosk experiment, Litmus agents are installed on EKS and OpenShift Containers platform. The Kubernetes platform are interconnected via a secure mesh fabric network with active and backup path configured as part of the policy. This is how the application's flow looks like. User connected to the F5 Distributed Cloud Network, which direct them to the front-end services hosted on Amazon EKS. These services access a backend database via a secure mesh fabric to a mesh node in Data Center 2. Additionally, the EKS environment access the money transfer and refer friends API services hosted on OpenShift Container Platform located in a separate data center. In the kiosk experiment, I will introduce a fault into the front-end microservices running on an EKS, causing significantly high latency and rendering the front-end unresponsive. These issues will trigger a redirection of front-end traffic from the internet to Google GKE. GKE will access backend database using the same secure mesh fabric. Similarly, GKE will access the money transfer and refer friends API hosted on OpenShift via the secure mesh fabric. Subsequently, I will intentionally deploy unstable releases to the money transfer microservices on OpenShift, causing money transfer to enter a crash loopback state. This scenario will prompt GKE to seek the money transfer API from Azure AKS as an alternate available services. Let's move on to the demo. Before proceeding with any kiosk testing, let's have a walkthrough of the demonstration environment. Here, I have enrolled and registered all the F5 distributed cloud mesh from respective different Kubernetes platform into the console. Here are the terminal view of the environment. For Amazon EKS, I have 2 worker nodes in the cluster. For OpenShift Containers platform, I have 3 worker nodes. For Google GKE, I have 2 worker nodes. And finally, for AKS, I have 2 worker nodes in the cluster. Here, I have the F5 mesh pod installed and operational on EKS, OpenShift, GKE, and AKS. They are all healthy and running and ready to handle traffic. A dedicated namespace called Acadia has been created. On EKS, the front-end microservice with a replica set of 3 instances are installed. On the OpenShift container platform, the money transfer and refer friends microservice are installed and running with a replica set of 3 each. This is to ensure local port redundancy for both EKS and OpenShift. Microservices have not yet been installed on GKE and AKS. This will be deployed later as part of the CI/CD pipeline to provide high resiliency for microservices. The on-premises virtual machine hosting the backend database is not displayed in this view. This Acadia Finance application is currently configured to be accessible from the internet. Respective load balancers and security controls have been installed and enforced, and origins pools have been configured. This is the FQDN for the Acadia Finance application, accessible from the internet. It is a sample financial applications where user can log in to perform trading activities. Currently, this application is being served from a heterogeneous Kubernetes cluster. Front-end served from EKS1, quick money transfer served from OpenShift, and refer friends from OpenShift as well. To implement kiosk engineering practices, I've leveraged the open source Litmus kiosk platform. Here is my Litmus environment with all the respective kiosk agent and infrastructure installed and connected. I also have executed multiple kiosk experiments to test the resiliency of my application and also have my resiliency props set up. Let's start by creating a new kiosk experiment or test to inject high network latency to the front-end microservice. I'm going to use Litmus agent installed on EKS1. The kiosk experiment starts with a blank canvas for flexibility in configuring desired kiosk. The Litmus kiosk platform allows injecting fault from a library of fault from Kiosk Hub. In this demo, I'm going to use port network latency, which disrupting network connectivity of Kubernetes port by injecting random network delays on the application replica port, causing flaky access to front-end microservices. I select target microservice based on label and inject 4 seconds of network latency to the front-end microservice. I also ensure injections apply on all the replica set. While injecting the fault, I also assign readiness probe to the application and ensure this probe continuously probing of the end-to-end application to monitor its availability status. Let's apply the changes and save the experiment. Here is the kiosk workflow of the experiment. It starts with install kiosk fault, then inject port latency, and do a cleanup at the end. Let's run the kiosk experiment. While waiting for the running kiosk to install necessary kiosk port and inject kiosk into the application, Let's test the front end to ensure it's still functioning. A KDA application is working end-to-end. Here is the request logs on the F5 distributed cloud console. It shows that front end still responding with 200 OK and healthy. Once the kiosk experiment is ready and the necessary kiosk port are injected, continuous access to the site via the kiosk prop will be observed from the logs. Kiosk 4 is installed and now it begins to inject port network latency. Continuous probe is running and waiting for results. Let's test the applications again. It seems like the application is not responding well. I'm getting a 503 service unavailable error. This indicates that our front-end application is unable to handle client requests if there's a 4-second delay on the network. This can be confirmed with the console logs. This is how we can experiment various network latency value to understand and learn the behavior of the application. Indeed, the application is down. Let's review the F5 district cloud logs to understand what's happening. From the logs, you can see that prior 503 error, front end on EKS1 is responding and subsequently it's failed. The kiosk experiment is complete and cleanup is underway. The application has reverted back to normal. While waiting for the cleanup of kiosk resources, let's experiment another use case where a CI/CD pipeline pushes a new versions of money transfer microservice onto the OpenShift platform and causing the money transfer microservice into an unstable state and crashed. Since the money transfer service is unhealthy and crash loopback, the front-end microservice is unable to retrieve API from the money transfer service, resulting in the coming soon display on the money transfer function. Front-end still working as no injected fault on the front end. From an end customer perspective, this effectively means that portion of the apps are down as user unable to make funds transfer. Let's revert back to the original state. In summary, the current demo shows that the application breaks the SLA if front-end network latency exceeds 4 seconds and no microservices redundancy for both causes the end-to-end applications to fail. Now application back to normal. Reviewing the previous network latency kiosk screen, the kiosk experiment failed, yielding a 0% resilience score. Before we commence another kiosk experiment, let's examine current F5 district cloud mesh configuration. Here is my API gateway for the backend, money transfer and refer friends. As shown, currently there is only a single site defined for all those pools. For the front end, similarly, we only have a single pool where it is pointing to EKS1. Now let's trigger a CI/CD pipeline to deploy a redundant copy of the front-end microservices onto Google GKE, while the money transfer and refer friends services deploy onto Azure AKS, each with a replica set of 3 for local port redundancy. These redundant copies are pre-deployed for quick failover. Event-driven orchestration can be done to deploy those copies on demand. I will trigger a separate CI/CD pipeline to update F5 Distributed Cloud Mesh Load Balancer to include these new sites' redundant microservices into the existing pools. What it means that F5 Mesh will do a service discovery to those newly deployed apps. Upon refreshing the console, new origin pool objects will be visible and they can be used as pool members for respective load balancer. Now, in the money transfer load balancer, Azure AKS updated as part of the origin pool. OpenShift as the primary indicated with priority 1 and Azure AKS as a secondary indicated with priority 0. Similar updates happens for refer friends load balancer. For the front-end load balancer, Google GKE updated as part of the origin pool as a backup pool for EKS. Routing and load balancing logic occur within the mesh pod in each Kubernetes environment. Backup member will only be used when primary member unavailable. Active-active can also be configured to distribute traffic to those microservices. With everything set up and ready, I will start a new kiosk experiment leveraging the previous configuration. Similar kiosk experiment started and running. Here, we validate to make sure that Acadia application is still functioning. Here's the XC request log show traffic activity. Kiosk is now ready to inject network latency into the front end. Let's observe the end-to-end application. Upon refresh of the page, you can see that now front end being delivered from Google GKE. This indicates that the kiosk fork injected onto front end microservice on EKS and is filled over to GKE. This also can be validated by filtering the source IP address from the kiosk prompt. From the logs, we can see that there is a 503 happening, and quite immediately, you can observe that it's returned 200 OK from GKE1. Upon the 4-second delay, front-end request being fulfilled by GKE. Subsequent requests will be handled by GKE until the kiosk experiment timeout and cleanup. Now looks like the kiosk experiment completed and cleanup happening. Front end back to the healthy and traffic redirected back to EKS. This traffic graph reflects multi-cluster, multi-cloud connectivity with traffic from the internet directed only to EKS and GKE for the front end. Connectivity to EKS and OpenShift via the respective front-end services. Backend database traffic is routed via a mesh node deployed as a virtual machine. The color of the traffic graph indicates health of those connectivity. Cleanup concludes successfully, achieving a resilience score of 100%. This showcases the effectiveness of F5 distributed cloud mesh for Kubernetes in ensuring end-to-end application resiliency, especially during network latency events. Now, let us move on to another probably common use case where a faulty version of application causes microservice to be unstable and crash. I'm going to trigger a similar CI/CD pipeline to deploy the unstable version of money transfer microservice. No changes to refer friends. Upon rolling in the new version, money transfer become unhealthy. As you can see, now money transfer microservice being served from AKS. Healthy refer friends microservice still being served from OpenShift cluster. In this demonstration, you had seen how F5 distributed cloud mesh able to help to ensure your modern application always available. Coupled with kiosk engineering practices, you can continuously test, experiment, and learn how your application react in a different scenario. At F5, we strive to bring a better digital world to life. Our teams empower organizations across the globe to create, secure, and run applications that enhance how we experience our evolving digital world. Feel free to reach out for further discussion. Thank you.